Hello, Geometry. This is Lesson 2 of Chapter 2. We're doing inductive and deductive reasoning. Exciting stuff. And the essential question here is how can you use reasoning to solve problems? And the two types of reasoning we're doing are inductive and deductive, and we're looking at how that plays into geometry and as we're doing our proofs. So just 4 vocab words in this section to pick up on. We have conjecture. Conjecture is kind of like a hypothesis. It is going to be an unproven statement. Now we can prove it using deductive and inductive reasoning, one of those two, but it's an unproven statement as based on observations. Unproven statement based on observations. So that leads us, when we're dealing with observations, things that we've seen, things that we've witnessed, that leads us into inductive reasoning. Okay? So that is when you find a pattern in specific cases and write a conjecture. Find a pattern in specific cases and write a conjecture. So your pattern might be, I haven't been watching these videos very well, but if you're watching it, that means you know that's not you, and I'm kind of struggling with my homework. So there might be a pattern of I'm not doing what I'm supposed to be doing, and then I'm struggling with my homework. So maybe I should do what I'm supposed to do, and maybe the homework will become easier. Okay? You're using inductive reasoning, looking at specific examples to come up with a conjecture. Okay, a counter example. This is a specific case for which the conjecture is false. A specific case for which the conjecture is false. So maybe it could be I did not watch a video, but I could figure out the assignment anyway. Okay, so that could be a counter example. Deductive reasoning is kind of the opposite of inductive reasoning. This is going to uses facts, definitions, accepted properties, and the laws of logic, which we'll cover a couple of them today, to form a logical argument. So it uses facts, definitions, accepted properties, and the laws of logic to form a logical argument. Okay, this is one using the rules, basically using the rules. So if we'd say all triangles have 3 sides, if I draw a 3-sided shape, you could say that's a triangle because we have the definition of a triangle to fall back on. If we say 2 points make a line, and if I draw 2 points, then you could say, hey, there's one line through there because we have the rule, through 2 points there is any line. Okay, so here we go with those core concepts. Here's a conjecture. So inductive reasoning. So let's say for 3 weeks there have been water cups at lunch every day. So you've been watching that, and every day they have water cups there for you. So you conclude your conjecture is there will be cups there tomorrow. So this part right here would be your conjecture. There will be cups tomorrow because you've seen the pattern and you feel like it's going to actually happen. Okay. So examples of counter examples would be if I have this conditional, if x squared equals 25, then x equals 5. And the instructions may say find a counter example. So is 5 the only number that we can square to get 25? So we think about that as what other number could we square? And the answer is x could equal -5. Because -5 squared is positive 25. So that would be a counterexample to this rule. If I run track, then I can run fast. Okay, there's lots of counterexamples to that one. Okay, fast is first of all relative. Okay, it depends on who else is in the race with you. Second, there are throwers, there are jumpers, there are distance runners, okay, which can run fast, but they're over, what's your definition of fast? Is your fast over 400 meters, or 3,200 meters, or 100 meters, or over hurdles? Okay, so if I run track, then I can run fast. And the counterexample is, I may not be fast, but want to be involved. Okay, I may not be fast, but want to be involved. That could be a counterexample. Deductive reasoning. Here we're using, let's scroll, there we go. Using the facts, definitions, accepted properties, and laws of logic to form a logical argument. Okay, so inductive is specific examples. Deductive uses the definitions. That's how I remember it. Deductive kind of uses definitions. Inductive uses your inside, is kind of how I always thought about it, like your gut, saying, I feel like it's going to happen this way. So deductive may say all reptiles are cold-blooded. Okay? Parrots are not cold-blooded, so we can conclude, based off our definition, that reptiles are cold-blooded, that parrots are not reptiles. Okay? That'd be an example of deductive. I have a definition that I'm using. I'm not looking at specific examples. Deductive, definition. Inductive, specific examples. Okay, here's some laws of logic, 2 of them, and then we'll look at some more examples. So the law of detachment. If the hypothesis of a true conditional statement is true, then the conclusion is also true. This is kind of like a, well, duh, of course. So our conditional might say, if you obey instructions, then you will do well. So you have obeyed. We're assuming this is true and the whole thing is true. Then you will do well. So many times people are wondering why things aren't going well, and you always have to go back and ask yourself, are you doing the right things? Are you doing the right things at the right time, with the right people, and at the right place? So that's the law of detachment. If you obey instructions, then you'll do well. You have obeyed. Okay. Another example, just out of the textbook here, question 8. More of a geometry one. It says if 90 degrees is less than the measure of angle R, which is less than 180, then angle R is obtuse. The measure of angle R is 155. Using the law of detachment, what statement can you make? So we know this statement to be true, and this is true with this right here. It fits in there. So we can conclude that measure or angle R is obtuse. So that one's not quite, that one's pretty easy to understand. The law of syllogism can be a little bit different, but it's kind of like the transitive property, if you remember that. If A equals B and B equals C, then A equals C. Okay? So they may say if hypothesis P, then conclusion Q, and notice the conclusion is the other hypothesis. So that has to be the same statement. If hypothesis Q, then conclusion R. So then this statement is true. If hypothesis P, okay, then you can pull this part down and this part down, then conclusion R. So the instructions there a lot of times say, write a new conditional statement. This right here is the new conditional statement using the law of syllogism. So it may say, if it rains, then I'll sleep. That's your first statement. If I sleep, then I'll dream. It is raining. Okay, what can you conclude? Well, you see, based off the law of syllogism, you see how this matches up with this right here. So if it is raining, then I'll dream. This is our new statement. If it is raining, then I'll dream. Now these two lines do not have to be written in this order. The bottom line can be written on top, and you'll see that in one of your questions. You may say, I think this fits this law syllogism, but they're going to put if I sleep, then I'll dream on top. Then on the bottom they say, if it rains, then I'll sleep. These can be written in any order. That is okay. Over here, if I drive, then I go fast. If I drive, then I get pulled over by the cops. Ran out of room there. So if I drive, then I go fast. If I drive, then I get pulled over by the cops. I'm going fast. This one you may say, hey, then I'm going to get pulled over by the cops, but this is an example of a no conclusion. You notice the conclusion of one of these doesn't match the hypothesis of the other. This does not fit the law syllogism. Does not fit the law syllogism. It would have to be rewritten as if I drive, then I go fast. If I go fast, then I get pulled over by the cops. Then we could say, if I drive, then I get pulled over by the cops. That conclusion has to match one of the hypotheses. Okay, here we go. Examples. Describe the pattern, then write or draw the next two numbers. So 20, 19, 17, 14, 10. Notice here, -1, -2, -3, -4. So describing, we are subtracting one more each term. The value there is term. Each of these are terms. First term, second term, third term, fourth term, fifth term. Next two numbers would be -5, so that'd be 5, and then -6, that'd be -1. So 5 and then -1. Okay, 2, 3, -3, +5, -7, +11. So this, let's try that again. That's -5. This one's +8. This one's -12. I'm not sure if this is helping. And this one is +18. 2, -3. So the next one has to be negative. You see how the signs are changing direction. Okay. I didn't look at this one. I thought I'd figure this out on my own. So this one is +13. That's +20. Sometimes you go to another level. That's not working. +30. Maybe some of you already have this figured out. You should tell me if you got it before I did. 2 to 3 is 1, 3 to 5 is 2, 5 to 7 is 2. 2 plus 3 is 5, 3 plus 5 is 8, that doesn't work here. There's always one more. Oh, let you figure that one out. I'll think about that one too. Here on the camera, I'm kind of under pressure. I want to get that one figured out. C, E, G, I, K, C, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Got that one. And on the assignment, make sure you know the months of the starting letters for the months of the year. There's your big hint on one of your questions. Okay, notice they're adding one line here, then they're adding two lines. So they're adding additional lines each time. This would have 3. 1, 2, 3. This would have 4. 1, 2, 3, 4. Okay, make and test a conjecture about the given quantity, the sum of two negative integers. So they're just saying, make and test a conjecture. So sum of two negative integers. Let's go -1 plus -2. That equals -3. -5 plus -8. That's -13. Oh, so we have two 3's. Do they always end in 3? -4 plus -3. That equals -7. So we're doing several examples here, and I notice they're all negative. So my conjecture is the sum of two negative numbers is another negative number. That's my conjecture. Sum of two negative integers is another negative number or integer. Okay. The product of three consecutive non-zero integers. So that's like 2 times 3 times 4. That would be 6 times 4 is 24. 4 times 5 times 6. 20 times 6 is 120. Non-zero integers. I'm just going to say it is larger than any of the three numbers, if positive. Okay? So that's what this is looking at, is just coming up with some examples that fit this criteria, and then coming up with a rule that says, okay, I think this is what we can conclude from that. Exercise 7 and 8, find a counterexample to show that the conjecture is false. Counterexample. So if n is a rational number, that's any number that can be written as a fraction, then n squared is always less than n. N squared is less than n. So counterexample would be let n equals 10. Then n squared equals 100, which is greater than 10. So n squared is greater than 10, which is n. Line Q intersects plane P at point Q on the plane. Plane P is perpendicular to line K. So we have line K intersecting plane P. There's plane P. And we want a counterexample. And that is not a 90-degree angle. Perpendicular says it has to be 90. It doesn't have to be 90. Here comes our laws. Use the law of detachment to determine what you can conclude from the given information, if possible. If triangle has equal side lengths, then each interior angle is 60 degrees. Triangle ABC has equal side lengths. This has to match the hypothesis, which it does. Equal side lengths, equal side lengths. So we can conclude each interior angle is 60 degrees. We can conclude that. So this statement has to match the hypothesis for that one. If a quadrilateral is a rhombus, then it has two pairs of opposite sides that are parallel. Quadrilateral PQRS has two pairs of opposite sides that are parallel. Notice this matches the conclusion. Let's go back up here. That must match the hypothesis. So this matches the conclusion, not the hypothesis. So this is a time when you get to say no conclusion. So this statement right here is matching the conclusion, not the hypothesis. Use the law of syllogism to write a new conditional statement that follows from the pair of statements, if possible. So this law of syllogism was that transitive property, if P then Q, if Q then R. Okay, so the conclusion for one statement has to match the hypothesis for the other statement. So if it does not rain, then I'll walk to school. If I walk to school, sorry, teams are about to arrive. If I walk to school, then I'll wear my walking shoes. So you notice how this matches this. So write a new one. If it does not rain, then I will wear my walking shoes. So final, if x is greater than 1, then 3x is greater than 3. If 3x is greater than 3, then quantity 3x squared is greater than 9. That matches that. So you can just say if x is greater than 1, then 3x squared is greater than 9. So put those together. And that's it for these examples. Let me know as you work through what kind of questions you have, and we'll keep working with this logic. This is completely different, isn't it? Okay, different than Chapter 1, and this seems a whole different realm for a math class, but it's kind of unique and special to geometry, the logic and reasoning, and what we're working with that. So I will see you soon. Good job. Good work.